welcome to today's colloquium. Our speaker is Dr. Aalen Shin. She received her BS and MS degrees in statistics from Seoul National University. She also received a PhD degree in statistics from Texas A&M. She joined the Biostatistics branch in National Cancer Institute as a postdoctoral fellow in 2017. And in 2020, she was appointed as a tenure track investigator. Her recent methodological research interests include spatiotemporal functional data analysis to model the risk of health outcomes. Welcome, Aalen.
Thank you for introducing me, and thank you for inviting me and giving me an opportunity to give a talk about my recent work. So today I'm going to present my two recent works. So it's kind of a combined talk based on two papers, but they actually share very broad theme. So the title here is Weight Calibration to Improve Efficiency for Estimating Pure Absolute Risk from Nested Case Control Design. So some may be familiar with some keywords here, but some may not. So don't worry, I'm going to go through one by one what the weight calibration is and what the pure absolute risk and so on. So I expect you can understand and get the sketch of the ideas at the end of my talk. So this is the joint work with Ruth, Barry, and Mitch. So it has started when I was postdoc in NCI, but some spin-off work is ongoing right now. So let me introduce the motivating example first. So suppose we are interested in estimating the association of the metabolites with the breast cancer risk in PLCO cohort study. So in this cohort study followed about 15,000 women who are aged in 55 to 74. So in this cohort, some basic information like age, smoking behavior, number of live births, a history of a benign breast disease, and BMI are available for all the people in the cohort, the capital N number of people. But the serum metabolites, which require expensive laboratory experiment, only available for the nested case control samples. So specifically, saying the small n number of people, which is the sum of the 620 breast cancer cases plus selected 620 matched controls are only available for measuring the serum metabolites. So this is pretty limited number of people who can have a certain information. So in this situation, our interest is in estimating the covariate specific pure absolute risk of the breast cancer risk. And here the pure absolute risk means literally just the probability that a certain event of interest occurs up to time t, which is given before analyzing. Well, it depends on the researchers. But here, most people do this estimation based on the regression model, and the popular regression model is for the hazard. The hazard, the lambda of t, is the derivative of the log of survivor function, and which is actually used to compute the pure absolute risk. So one more comment about the pure absolute risk is actually the reason why I put pure here is I assumed the very simple situation that there is no competing risk. So if there is competing risk, then this became just a general absolute risk. But because I'm going to just go through some methodological aspect of the estimation. So let's just assume the very ideal situation without any competing risk. So that's why I said just pure absolute risk here. But all the methodology that I introduced in this talk can be extended to the general absolute risk by incorporating the competing risk later. So the popular model, the popular hazard model is first the proportional model, introduced by Cox in 1972, which is the product of the baseline hazard lambda naught of t times the relative risk exponential of the beta x beta in my note. And the second option could be additive model when the assumption for the proportional model does not hold. Then additive model can be used, which resembles just a linear regression. So it could be just the x beta, but still the outcome is a hazard function. So now the research question with this research interest and setup, our question is, can you use all available data, the capital N number of people in the cohort, instead of limiting just a small N number of people? And the answer is yes. And the technique that I'm going to use is weight calibration. So these red colored keywords, nested case control sample, pure absolute risk, weight calibration, you are going to hear these words a lot of times in my talk. And well, I'm going to introduce the nested case control sampling first to go to the next step. So here is the nested case control design introduction, which is one of the most popular cost-effective studies to obtain some expensive exposure, which was serum metabolite in my previous example, for a subset of a larger cohort. So I'm going to use the term phase 2 for a subset and phase 1 for a larger cohort. So let me give you just a simple example. So suppose there are 10 people in a cohort and we're going to match 2 controls per case. Then this cohort developed 3 cases, the ID number 1, 3, and 7. And then you can see the remaining people didn't develop cases, so we can consider them as censored at the time of the study we did. So it could be like this time point, for example. So they are noted by cross here, and then you can see, for example, at time T1, which is the case time, the first case time, then this example select the ID 3 and 5 from the set of the people who are at risk at time T1. So, and later, likewise, we select the 2 controls at T2, T3, which is the second case time. And this example sampled the number 5 and 8. So likewise, we sample the people every time a case develops. So, and you can see selected control can develop case later, or selected case can be selected again for at the other cases time. And this type of sampling is also known as risk subsampling or incidence density sampling, just in case you are more familiar with the other names. So I redraw the structure of the data set instead of using the follow-up time lines. So this is the basic structure of the 2 phases study, and especially for the nested case control design. Suppose from 1 to small n's are selected the people by nested case control sampling, then we will have the capital N number of people who had the survivor data information, like the follow-up time, whichever comes first between case or censoring, and delta means the case indicator based on the event of interest, which can be computed based on the counting process. And then also some covariate denoted by X here is available for all the people in a cohort. I said that as phase 1 covariate, and Z1 type of the covariate is only available for the small n number of people. I will call it phase 2 covariate. So in this structure, Samuelson in 1997 computed the sampling probability weight, which is just the inverse probability weight, to compute the inclusion probability pi here. So for the cases, it is always 100% included, because case is always, case plays always the important role in the risk analysis. So they are always included into the nested case control. But for the non-cases, they have a chance to be selected or not, and Samuelson provided the computation for that inclusion probabilities. So the basic idea is that this type of probability estimation is Kaplan-Meier type estimator, so that you can interpret it as that is the probability that can be selected at least once by subtracting the probability of being never being selected as a control from one. So that's the idea of the pi, and well, the main point is we are going to use the sampling weight for the nested case control design that Samuelson proposed as here. So let's come back to the data structure here and talk about what other standard approaches did for this situation. So most people use just the phase 2 data only, and they just drop these data. N+1 to capital N number of data were just ignored in their analysis, but that is apparently inefficient, I would say. So we want to incorporate the phase 1 data, including everything, to improve the phase 2 analysis. So let me quickly summarize the some statistical method for doing so. And here are 3 methodologies. The first one is maximum likelihood estimation, which is also really popular. But I just summarize these methodologies in terms of computation and sensitivity on to the assumption on the conditional distribution of the missing variable z. So for the maximum likelihood, I would say that includes really complex computation. Well, if you're familiar with this situation with missing variable, then maximum likelihood includes some EM algorithm, and usually each step requires mathematical derivation, which is usually complicated and really heavy, and also the computation time goes really long to solve that each step usually. Not always, but well, that can happen a lot. And also the other issue, the concern regarding to the maximum likelihood is the sensitivity on the distribution or assumption. So if the assumption for this conditional distribution goes wrong, then well, it is likely to have something problem in the final estimation we are interested in. So that is the quick summary of the maximum likelihood, and the multiple imputation could be the option, the alternative of the maximum likelihood. And this is really brilliant idea in terms of the simple computation. It just impute the missing part of z multiple times and take just the empirical mean of those multiply imputed and estimated quantity, and that's the how they make the estimation in the end. But still, this approach is pretty sensitive on the assumption of the missing variable. So if this conditional distributional assumption go wrong, then the final estimation goes also wrong. So well, that risk should be taken when people do this type of methodologies. But here, the way calibration that I will focus on this talk is also simple in computation, and the best advantage of using this methodology is robustness to the assumption on the conditional distribution. So let me look into the weight calibration method and how they could be robust. So suppose the statistic GI is a certain function of the data we have, so it could be any, and then we are interested in estimating the theta hat, which is the full cohort, the sum of the GI. But here I denoted in this way very simply, but practically in the nested case control design, this term is not, this estimator cannot be obtained because the missing in z covariates. So this capital N number couldn't be summed up. So the basic approach is to get the sample weighted sum using the sampling weight, as I just introduced how the Samuelson calculated the sampling weights for the nested case control design especially. But this approach has limitation because it uses only complete phase 2 data. So again, they drop all the other information out of the phase 2. So the here is calibrated weighted sum. So it merely substitute the sample weight into the calibrated weight, the W star I denoted. And this calibrated weight can incorporate the phase 1 data. So this is the basic idea, and the robustness is guaranteed as long as the sampling probability is well defined to be consistent. So this is the algorithm to get the calibrated weight, W star, which is the argument that minimizes the sum of the distance from the sampling weights. And distance can be defined by your own, or it could be just a simple distance that people usually do. So let's say just the general distance quantity between weight and the fixed sampling weight with, and we do this optimization with a constraint that the phase 2 sum and total sum in phase 1 are equal. Here, the AI is actually auxiliary statistics, which is available in phase 1. So it could be any, but the only requirement is that these auxiliary statistics should be available in phase 1. Then we can build up the phase 2 weighted sum and the phase 1 total sum. So the point of this calibration is that the calibrated weighted estimator theta star head is more efficient than the sampling weighted estimator theta 0, which means mathematically the variance of the theta star head is smaller or equal to the variance of the sampling weighted estimator. And it gets more efficient if we have the auxiliary statistics, which is correlated with the GI, which is the original interest of the original estimate of interest. So if we have, we can find the AI, which is more correlated with GI, then we can get more efficient with the calibrated weights. So again, the key is to find a good auxiliary for the estimate of interest, which is covariate specific pure absolute risk in our study. So to get this estimate, we're going to consider two model framework. First one is the proportional model, and the other one is the additive hazard model. So let's go to the proportional hazard model framework first to get the pure absolute risk. So the Cox hazard model is the product of the baseline hazard and relative risk using the covariates and coefficient. And this coefficient is actually called log relative hazard, which can be obtained by maximizing Cox partial likelihood. So if you ignore this red color part, this is exactly the Cox partial likelihood. But because of the limited data, we just weigh up the data set to the full cohort using a certain weights. So here, let's say just very generally, just the W1. And the baseline hazard can also be estimated fully non-parametrically by just counting the number of cases divided by the weighted sum of the relative risk. So here I denoted it by W2, but the W1 and W2 could be same. So it's up to the researcher, but I will go into how we can define these W's more specifically. And then finally, once the beta head and lambda node head were estimated, then we can combine those estimates into the pure absolute risk for a given X and Z covariate level by transforming the hazard into the pure absolute risk. So this is just the framework, and let me give you the summary of the literatures regarding this framework. So the Langers and Bourgain consider the pure absolute risk in the nested case control design, but they didn't actually use this likelihood, but just the Cox, the conditional logistic regression. So that's why I denoted it just the NA, but still, in principle, if you just did without any weights and just do the construct the likelihood only based on the subset, then that is that gives the same estimates that conditional logistic regression resulted in. And the idea of the language program's paper is actually this way, which is way up the risk set size. So N of T is again the risk set of the risk set at time T. So it can be defined at any case times. This is kind of the size of the sampling pool, and the M is the number of samples where the number of samples at each time point, and it was always fixed for every case. So they, by weighing up the denominator of the baseline hazard with this weight, language program could estimate the baseline hazard, and finally, using the conditional logistic regression estimate, they could estimate the pure absolute risk. That's how language and program did. And Samuelson, at the very similar time, he was interested in estimating the log relative hazard in nested case control design, and as I introduced earlier, he proposed the calculation of the sampling weights, which is the inverse of the inclusion probability, so that he estimated the log relative hazard. And later, Breslow and other researchers in 2009 was also interested in beta, but in case cohort design, which is also popular in epidemiological cohort study, but slightly different from the idea of the nested case control study. But well, it is also type of a two-phase design. So you can think there is a subset of the cohort by doing the case cohort sampling as well. So they proposed some calibrated way to get the beta more efficiently by incorporating the phase 1 data. Unfortunately, not unfortunately, I'm sorry, the Breslow actually didn't consider the baseline hazard or pure absolute risk, but the new thing that I did in my recent study is incorporating the idea of the Breslow and other researchers, and additionally, I incorporated more information that Breslow actually missed in their study. So last two papers considered the way calibration to incorporate the phase 1 data. In that sense, they share the same similar idea, but let's look into what they did and what I did in the next slide. So this is quick summary. So let's say the U is ancillary predictor for the missing variable Z. So this is not the model covariate. This has nothing to do with the hazard directly, but this is very useful to make the prediction of the Z tilde, so which plays a role with the conditional distribution of the missing variable Z here. And using a certain prediction model we construct for the prediction, we can predict the Z variable even for the missing part, and I will call it Z tilde. And then we can get the log relative hazard estimate beta tilde here for the X and Z tilde that are now available for the phase 1. So based on this estimate, the influence function can also be computed, and let me tell you what the influence function exactly means. And this is just a quick summary of the influence function. That is the linear approximation of the estimator. So in terms of beta, you can just make the linearization of the beta head into the sum of the data. So in this regard, we can get the individual impact of the individual impact of the data on the estimator. So Breslow calibrate the sampling weights using this influence function to obtain the W star. So this idea is actually beta head can be expressed in terms of the sum of the GIs, which is unknown in practice, but that can be approximated into the sum of the influence, which is really brilliant. And it really improved the estimation of the beta head. And now what we did is to add one more auxiliaries that is based on the follow-up time in the risk protection interval. So usually people just set up the risk protection interval when calculating the pure absolute risk. So let's say tau 0 to tau 1. So it can be just to make it can be calculated by summing up all the at-risk indicator within this time frame. So this follow-up time can be used in building another auxiliary variable, and my proposal was the multiplication of the time tau I times the relative risk, which is made from the z tildes. So they are now available for everyone. So one more remark that I would like to make about this auxiliary is that this additional quantity is actually integrated denominator of the baseline hazard estimate, and this quantity is considered as the sum of a certain quantity in the full cohort, and we approximated this term into this product. So please note that the numerator of the baseline hazard is just the number of a case, which is always known and which doesn't need to be imputed or doesn't need to be estimated at all. So we just directly focus on the denominator part only. And also another remark is using the ancillary predictor for Z can improve the efficiency of estimating beta 2, which is the coefficient of the missing variable Z. And this can improve the efficiency of these estimates when there is non-zero correlation between Z2 and U. So we will see how this can work in the simulation in a moment. So let's move on to the additive hazard model framework as well, which resemble the linear regression. So I hope you can just quickly get the idea of the estimation. So in this formulation, I didn't separate the notation of the covariate into X and Z based on whether they are included in phase 1 or 2. But here I just separated the covariates into X and Z based on type of the coefficient. So X covariate regards to the time varying effect, and the Z covariate have a time invariant effect. So in terms of linear regression, time invariant coefficient could be understood as just the slope, and time varying coefficient could be understood as just the slope. I'm sorry, the intercept. So first, we estimated the slope, and then using that estimated slope coefficient, we calculate the intercept. So that is how the additive hazard model framework estimates its model coefficient. So the one more addition is that this is weighted regression. So we have the diagonal matrix of the weights here, and well, H of T denotes the perpendicular projection, like I just noted here, but the details not actually the main point of this estimation, but just to remember, there is the similar formula to the linear regression. So once the gamma and the beta, so here the beta is also estimated fully non-parametrically using the jumps. So that's why I denoted it D capital B hat of T instead of using the continuous function like beta of T. So finally, we can estimate the pure absolute risk of what we did for the Cox proportional model framework, so that we can get the pure absolute risk in the end. So here is the summary of the literature review, what people do with this model framework. And very recently, the Breslow and Hu considered a very simple model of the additive model. That means they didn't actually include any time varying effect in the model, but just included only the intercept part, beta 0. And they just summarize all the effects into the time invariant coefficient, the gamma. So the main interest was on the gamma. And the Breslow and Hu consider the case cohort design with the calibrated estimate, the calibrated weights. And Summers and Store also did very similar thing for the same model without any time varying coefficient except the intercept, which is baseline hazard function, but interested in the gamma in the nested case control design. And we extended their idea to our study. So we considered the very general case of the additive hazard model, which can include the time varying effect in terms of the beta t, not just beta 0t, the baseline hazard. And then our final estimate was actually pure absolute risk in the nested case control design using the calibrated weights. So this is the quick summary of my second paper in this talk. So the beginning is pretty similar. We just prepare the auxiliary predictor, which is not model covariate for Z, but usually Z is very expensive, but U is very cheap thing. So that can be usually available for everyone in a cohort. And Z tilde can also be computed by the prediction using the prediction model based on the assumption of the conditional distribution of the missing variable given other information we had. So finally, based on this Z tilde and X, which is already available in phase 1, we can get the linear coefficient estimate and calibrate the sampling weight using the influence function of the gamma tilde to obtain the W star, and this substitutes the estimator directly. But what we added is the integrated term of the influence function of the d beta tilde, and I have some, well, the idea is pretty similar by linearizing the estimators, but the main point could be on the interpretation of this addition, because the influence function, I didn't specify all the details of the influence function of each estimator, but the point is that is proportional to the integration of the at-risk indicator Y and covariate X based on the martingale residual process. So in this regard, if you think simply the Xi is just an intercept all one, then this is exactly what we did for the follow-up time in the risk projection interval we did for the Cox proportional model, so that we can say survivor information, the time to event is incorporated into the calibrated weights. And another remark I want to make is that this additional auxiliary is numerically and theoretically perpendicular to the existing influence function, the auxiliary variable. So I can go into how they can be perpendicular, but well, someone may be really familiar in the relationship between slope and intercept. So they are automatically perpendicular. So that the summary is that the additional auxiliary is unused in previous work. So the additional information and the existing information have no overlap. So they guarantee the improvement in estimation, especially for the pure absolute risk. So I'm not going through all the asymptotic parts in detail, but the point is this lemma in my paper proved the design consistency of the weight calibrated estimator. So the design consistency means that weight calibrated estimator goes to the value that actually full cohort estimator would go when the sample size go infinite. So that is called as design consistent, and well, based on likewise other theorem proves, based on, well, suppose all the conditions hold, then we can show that using the triangular inequality, the first term goes to 0 as the capital N goes to infinite, and the second term also goes to 0 as the sample size goes infinite. So that is just a quick sketch of the proof, but the point is this guarantee the robustness of the weight calibration technique unlike the other approaches that can handle the missing problem. So once we could obtain the sampling weights that is design consistent as well, like Samuelson provided, Samuelson actually proved the consistency of the sampling weights, but we also showed that the weight calibrated estimator is always consistent to the full cohort estimator in this lemma. And also we provided the variance estimation of the weight calibrated estimator. So I'm not going through every parameter, every estimates, but in general, I just use the theta notation. And this could be structured by two terms. First one is weighted term because some elements were only from the phase 2, and BI term is available for the phase 1. So all the influence of the weight calibrated estimator have two terms in terms of the very simple structure, and this will be used to approximate the variance of the theta head. Although people can just do the bootstrap or other empirical approach to get the variance, but we preferred to get some explicit form of the variance for the practical use instead of learning all the bootstrap things for the two-phase design. So one of the challenging thing in the nested case control design is that there is a negative correlation between two distinctive units. So we therefore cannot ignore the joint probability of subject I and J, which are not same. So we have to compute the sigma ij, which denotes the variance of the sampling indicator of two subjects. So considering this dependency, we did the variance decomposition, conditioning on the full cohort. So in summary, well, this is exactly the approximation of the variance of the calibrated any estimator, but it can be decomposed into two parts. The first one is the variance of the conditional expectation, and the second one is expectation of the conditional variance. So you can interpret the first term as just the superpopulation variance. That means it takes into account the variation from the random cohorts from the infinite population. However, the second term considers the phase 2 sampling variation given a cohort. So you can see we measure the variance of the sampling when a cohort is already given, and then we just took the expectation of that. So this is the analytic form of the variance, and we can finally get the estimation using the data. So this can be practically used to get the variance of the estimates. So AI came from the phase 2 and BI came from the phase 1. So each of the estimates, it could be pure absolute risk in the end, but well, intermediately, it could be log relative hazard or linear coefficient in the additive hazard model. So we derived all the details of the AI and BI so that people can directly put their data into that structure to get the variance simply. So let me go to the simulation study first for the cost proportional model. So we have just the two covariate X and Z is just a phase 2 covariate that is missing in phase 1. And I compared the 4 phase 2 analysis. So you can see that there is a full cohort estimation at the left, which is in practice not available because missing problem. So in the simulation, but we can generate the full cohort and pretend the part of the Z covariate has missing. So the relative efficiency is defined as the relative efficiency to the full cohort estimation. So that's why you see the 100% efficiency for the full cohort estimation. And the Langersbergen's approach and Samuelson's approach, who actually used only phase 2 data that are complete, has a little bit limited relative efficiency in estimating betas. So that is the how I draw this figure, and you can compare other approaches that Breslow did, which focuses on estimating the log relative hazard rather than baseline or pure absolute risk. And our approach improved everything, not just the beta, but also the baseline. And then finally, we could see the improved efficiency for everyone. So these improved efficiencies are translated into the pure absolute risk. So I just included four selective combination of the covariates. So the summary is that beta 1, which regards to the covariate that was available in phase 1, fully improved by incorporating this variable into the influence function of the beta head. And the beta 2 can also be improved by incorporating the ancillary predictor U. So in our simulation setup, their correlation was 0.8. So you could see this purple line goes up when we calibrate the weights based on the influence function of the beta 2 as well. So if we have just a zero correlation, we would not see this increase, but it goes just, very similarly as Langworth-Burgan and Samuelson did. And lastly, the baseline hazard actually lose the efficiency by doing the Breslow's approach because they just adjust the weights only toward the beta's efficiency. But we considered everything, including beta and the baseline. We recover the efficiency of the baseline to almost fully the efficient, so that we can say the baseline hazard and covariate specific pure absolute risks are improved by additionally incorporating follow-up times into our specific form of the auxiliary variables. So I didn't include all the numbers, but I can say the coverage rates were also all 95%, around the 95% using our variance estimation formula. So this is the take-home message of this simulation study. Our proposal is the most efficient for estimating pure absolute risk at all covariate levels. And let's go to the simulation study for the additive model. And now it has the formulation X beta plus Z gamma. So the comparison is very similar as we saw in the Cox proportional model. We compare the three phase 2 analysis. One is for the sampling weighted approach. Well, here should be 0 if I followed my previous notation. And W star gamma means that the calibrated weight using only the Z information instead of considering this part. And the last one, which is our ultimate proposal that calibrate toward every coefficient we have in the model. So you can compare all the model parameters in the left figure, and the right side I also selected for representative combination of the covariates, and you can see the very last one has the most efficient performance in estimating each of the estimates. So this is just explanation of the X and Z. Here, X actually include the intercept to include the baseline hazard, and I assume the Z2 is only available. So that's how we have the fully improved estimation except gamma 2 by incorporating all the information we had in phase 1. And gamma 2 can also be improved in this simulation setup by incorporating the ancillary predictor U, again with 80% correlation between missing variables Z2 and U. So again, the conversion rates were around 95% using our proposed variance estimation formula, and the last message is very same as before. So let's come back to the data example, the breast cancer risk analysis in the PLCO cohort study. So the very first question we should answer is actually which model should be used between proportional versus additive. So one can do some kind of Schoenfeld test that actually tests whether the assumption for the proportional hazard model holds or not. So in this example, we found that the additive model follows better than the proportional one. So we chose the additive model for this example. And the next question is then, if the additive model is correct, then which covariate should which type of coefficient, time varying versus the time invariant. So we can do also some existing test, which is not our actually focus, but practically that is required prior to the analysis. So we decided to, we made the model like this. The breast cancer risk is the outcome, and we have two time varying effect regarding to the number of births, and we have time invariant effect for the remaining variable, including the smoking behavior and a history of the benign breast disease. And the last one is the one of the serum metabolite that is known to affect the breast cancer risk. So apparently, this variable is the Z2, which is only available for the nested case control sample. And there is a paper in epidemiology that BMI is associated with this certain metabolite. So we took that knowledge as an ancillary predictor. And in our phase 2 data set, we could see the correlation between BMI and this certain serum metabolite has 75%. So the bottom figure shows the time varying effect of the number of live birth covariate. And well, it is really interesting, so I included it. You can see the young women have the less likely to have the breast cancer risk if they had one birth in their lifetime, but if they got older, and they have more likely to develop a breast cancer likewise. But however, if they have the 2 or more births in their lifetime, and always the effect of this covariate is negative, that means they are less likely to develop a breast cancer in their life. So we can see apparently the time varying effect for this covariates. So now let's see the result for this example. And I just selected 4 women depending on different combination of the covariates. So for example, the first woman is nulliparous, never smoked, had no breast disease history, and the serum metabolite has the level -0.2. Likewise, I make some difference combination in this way. And also I compare the 3 methods here. Please note that we don't know the full cohort estimation here because this is the real data example. So we first estimate the sampling weighted estimate, which uses phase 2 data only, which is limited in our research question in terms of that. And we compare the calibrated weighted estimator into 2 types. The first one incorporated only the covariate information in phase 1, but the last one incorporated all the covariate information and survivor information that were available in phase 1. So this is the result and summary. So you can compare the 4 estimates, R1 to R4, and you can find that all the point estimates is unbiased. That means although we use some prediction model, we see the robustness character using this weight calibration. So the point is that point estimates are unbiased even after the weight calibration applied. And another point is that using our variance estimation technique for every method, we see the last one, our ultimate proposer has the shortest confidence interval. That means our proposer, the cross mark, is the most efficient. So that is the take-home message of this slide. So let me summarize my work. This is the first study of the weight calibration to improve exposure-specific pure absolute risk estimates. from the proportional and additive hazard model with the nested case control design. So in summary, all the information, including chip auxiliary, denoted by U in my talk, and survivor information like follow-up time T information, which were available in phase 1, are additionally incorporated to calibrate the sampling weights. So in specific, to be specific, the proportional model framework actually improved not only the relative hazard, but also the baseline hazard. And for the additive hazard model, not only the time invariant coefficient, but also the baseline hazard and time variant coefficient were also improved. So we also provided and derived the design consistency and variance formula of the weight calibrated estimates. And I can say the future studies can focus on more complex two-phase design other than nested case or case cohort design, or it can consider other model frameworks like Aalen that combines proportional and additive model, and also the fine-grained model could also be considered, which directly regress the covariates to the absolute risk instead of the hazard. So that could be an interesting topic in the future. So this is the end of my talk, and thank you for paying attention to my talk. And this is the list of the literatures that I introduced, and please take some notes if you want. Thank you very much.
Thank you, Yayan. Thank you. Any questions for our speaker?
Do you have any questions? Is there any misleading parts that I said or some other comments do you have?
Well, we can you can end the talk, and if anyone wants to talk to Yayan individually, you can just stay around and you can discuss.